Okay, last time we discussed about gauge transform. This was our last topic, right? Gauge transformation. I introduced to you two gauge transformation, the column gauge and the Lorentz gauge. And how do we actually make use of this? So let's go back to the general form of the Maxwell's equations. Okay. So we have del dot E. This is rho over epsilon naught. So these are actually the four Maxwell's equations. When we solve the Maxwell's equation, what are we solving for? Okay. Well, certainly we are solving for E and B. But the problem is that E actually has 3 components and B has also 3 components. So that means that we need 6 functions here. Ex, Ey, Ez, Bx, By, and Bz. And these are all functions of x and x, y, z, and t. Okay? Actually, it would be, if we formulate things in terms of the scalars, or in terms, not scalars actually, in terms of potentials. Okay? Why? First is that potentials are actually more fundamental than the fields themselves. Okay? It's actually potentials that generate the field. But, kumbaga pa, we could not directly measure the potential. The effect that we measure, in order to measure something, we need change of motion, diba? So we have to test something there. Like for gravitation, you have test mass. For charge, you have, for electricity and magnetism, you have test charge or a current. And tanawin niyo asa siya directed ang effect. Now, okay, first is, let's deal with this one. In vacuum, these are actually 0, 0, and this is 0. Okay? But in electrostatics, okay? In electrostatics, what do we have? In electrostatics, we have del cross E equals 0. But in electrodynamics, no. Del cross E is no longer 0. In fact, it's actually equal to the rate of change of the magnetic field, no? So therefore, when del cross E equals 0, what are we trying to... in electrostatic, del cross E equals 0, right? So in this case, we can say that E is actually a gradient of a scalar, right? A gradient of a scalar function, we call that the potential function. But the problem is that we are now in electrodynamics. So, sa ato pa, del cross E is no longer 0. So, in electrodynamics, okay, clearly, del cross E is not equal to 0. In fact, this is now the equation of del cross E. So, but still, B is divergence-less. So in fact, with this one, we can still use B, since del dot B equals 0, we can still use we can still let B to be del cross A. And we already, we call this the vector potential. Okay, the vector potential, we use this one in order to calculate for magnetic fields, right? But there's a problem with that one. The vector potential is not unique. For a given configuration of magnetic field, you can have multiples vector potential that would give rise to that kind of field. So it's not unique. That's a problem. But anyway, it simplifies. It's actually a mathematical tool to simplify the calculation. But in reality, we are not actually concerned with A. We are interested with B, the magnetic field. Now, using this, okay, if we substitute this one, substituting this one to this equation, plugging in what do we have? Del cross E equals what? Minus partial over partial T, del cross A. And we can actually interchange this del here. Okay? So we have now minus del cross partial A over partial T, and grouping on the left side tanan, we have del cross E plus partial A over partial T equals 0. So this is a vector field, which is the curl of that vector field is 0. So ato pa, it's we can think of this as this vector field now, E plus partial A over partial T, as some vector field which is actually a gradient of a certain potential, scalar potential. And we use that fact that this is the, so sa ato pa, this whole thing here is that E plus partial A, therefore, E plus partial A over partial T must be a gradient of some scalar field. Okay? It's a gradient of a scalar field. And so we can actually express it in terms of the scalar functions, of the potential functions. We have now minus del phi minus partial A over partial T. This is now the electric field in terms of the potential functions. Okay? And substituting this one, balik dire, no? We use these two equations. What do we get? Okay? Okay, pag-erase ani kay lahi na dito. Kita tag katong nindot nga eraser bi. Kinsa na i-cloth dira nga kanang murag kanina lang sa. Okay. When we substitute this one to substituting this one to this equation, what do we get? Del dot E, del dot what? Del dot minus del phi minus partial A over partial T equals rho over epsilon naught. Okay. And what do we have here? We have what? Okay, del squared, ating ibalin dire ang negative. So del squared phi plus, we have partial over partial T, we interchange del dot A equals minus rho over epsilon naught. Okay, so this is now the first equation. How about the second equation? This one, the fourth equation. This would become, on this side here, we have, what's del cross B? What's B? That's del cross A. So ato pa, del cross A equals, okay, mu naught J plus mu naught epsilon naught times, what is, okay, sorry, this is partial over partial T of what? This is minus del phi minus partial A over partial T. Okay. So, this is actually purely mathematical nga mga nga mga manipulation. You can just do this. There are lots of derivation on this one. But anyway, just to show you. Okay, first, what is this? Identity. This is what? This one. This is del dot A, right? Minus del squared A. Okay? Now, let's move this one to the other side so it becomes a plus, no? So, plus what? And then, we take interchange this one here, and then let's use this as 1 over c squared, right? To simplify the notation. And you have, we move this to the other side, so, sa ato pa, this is, this is del partial phi over partial T plus 1 over c squared partial squared A over partial T squared. And this is equal to, this is mu naught J. Now, we can group similar, like this one as a del, this is a gradient. No, this is a scalar, right? So this is a gradient of a scalar, and this is a scalar, so this is a gradient of a scalar. So we group this term, and what do we get is we have del, this is del dot A plus this 1 over c squared partial phi over partial t. Okay. And how about this one? Okay. This is minus del squared A plus 1 over c squared partial A squared, partial squared A over partial t squared. This is equal to mu naught J. I think this is correct. Yes. Now, we are in this equation has just transformed from the electric and magnetic fields, it transformed to the potential functions. Okay? The scalar potential function and the vector potential function. Okay? And the thing about this is, well, it looks, ano siya nga, ganun gato maninggi, ano diri nga, nag-complicate naman noon, no? Yes, actually, it turns out to be more complicated. Pero actually, kung tanawon ninyo, actually, this is less complicated. Why? Our two equations are now in terms of phi and in terms of A. How many terms does A have? You have three components of A. AX, AY, and AZ. And you have phi as a scalar field. So, isa lang. You actually need only to determine 4 functions. Whereas, originally, you have to determine 6. No, but actually, 4 out, reducing 6 to 4 is not, well, it's an improvement. Okay? But we can simplify further. And since, remember what we talked about gauge invariance. Right? What's the significance of gauge invariance? Well, we can transform, we can add something to the potential. No? Where are we adding it? Why are we adding something to the potential? And it's actually we are adding a gradient of a scalar function, right? Why? In order to, well, in the aim to simplify the problem. The thing about that is that we have gauge freedom here. This is, di ba, for any given A, I mean, for any given configuration of B, no, you can actually have multiple A's that will lead to that B. So I can actually choose some A. Well, you have this A, you have this A, and you have this A. You know, you can have many A's. In fact, it could be infinitely many possible choices of A. But you can find the simplest function to do that. Well, maybe that's not the simplest function because we cannot actually do that. But somehow, if we know these functions, candidates, what we want is actually the simplest one, right? No? The same with the potential phi. Now, since we have what we call, this is an equation of, these are equation of potentials, we have gauge freedom, we can actually choose we have the freedom to choose some things to be some things that must be satisfied. No, because we can choose A and phi. Now, in this sense, we want to choose such that this will simplify, this equation will simplify if this whole thing here will be 0. Right? So sa ato pa, we want to choose the gauge in which this whole thing here is 0. Why? Because this equation would simplify a lot. And in fact, what do we have here? We want to impose that del dot A equals what? Minus 1 over c squared partial phi over partial t. And this, by imposing this, okay, this now becomes 0. So this equation here, the Ampere's, modified Ampere's law, okay, becomes what? Only this equation here, because this is 0. And this thing here is what we could, this gauge is actually what we call the Lorentz gauge. No? This is the Lorentz gauge. I introduced it to you last time, but wala kaya na ako na-explain pa kay muraganig ang explanation niya. In fact, I mean the beauty of the gauge one, of the gauge of gauge invariance and gauge freedom is actually when we use them to simplify things. And by that time we were not solving equations. Okay, so this is the Lorentz gauge. In fact, the other gauge is actually what we call del dot A equals 0. No, the column gauge. Now, I will not do the column gauge. I will formulate things in terms of the Lorentz gauge. In fact, the column gauge is actually used in electrostatics, but when we are in electrodynamics, we are using Lorentz gauge. Now, are there any gauges here? Yes, there are actually many other famous gauge transformations, no, that would make this but these are the two kumbaga pa pinaka-famous. In Griffiths, I think only 2 gauges are mentioned. Lorentz, did he mention other gauges? Wala, no? Okay. Now, take note of what I'm doing here because ako nang ipabuhat sa inyo, ha? Okay? I will let you do the column gauge in the exam. How would the equation transform when we are using the column gauge? And in fact, you would realize that column gauge is actually in the electrostatic condition. Column gauge works well there. Okay? So here, okay. So by imposing the Lorentz gauge, we have this equation. And how about this? What would this? Asa itong isa? This one here. Okay? This equation would transform. Napay. Okay, kanilang sa kaya pa man. Nindot lagi ni siyang eraser. Magpalit lang tag wet wipes, no? Okay. I'll take note here, the Lorentz gauge. The Lorentz gauge is actually what? Del dot A equals negative 1 over c squared partial phi over partial t, or this is actually mu naught epsilon naught, right? That's mu naught epsilon naught there, no? I think Griffiths introduced it as mu naught epsilon naught. Okay, but anyway, mu naught epsilon naught is 1 over c squared. So, what happens to this one is this, right? Del squared phi plus, so mahimo na siyang minus 1 over c squared,
partial squared phi,
and you have now partial squared phi over partial t squared equals minus rho over epsilon. This is what? This is the Poisson's equation, right? That's the Poisson's equation. Well, it said it doesn't look like the Poisson's equation. Why? Well, you know the Poisson's equation to be this, right? That's the Poisson's equation. But we have this form here. In fact, this would make sense. This is still the Poisson's equation. That's the 4-dimensional Poisson's equation. Okay? And, okay, we have 2 equations. The first one, this equation, kanisha, would be that equation. And this equation would be what? So, ganito. Kalimot na ko. Itong dire. Del squared A ba? Del squared A plus 1 over c squared partial squared A over partial t squared, right? Sakto? Equals minus mu naught J. Gimove na ako dire negative. Sorry, na dire negative bro, no? I'll move the negative there. And there's something, this is actually, the 2 are similar equations. Diba? Now see how the equation transformed by using the column gauge, right? The Lorentz gauge. Now, of course, you should also try in yourself later, what would be the equations if we use the column gauge? Okay, in fact, this is what we need for now in order to to move into the concept of four-dimensional vectors. Let's look at the column, the Lorentz gauge. If we examine this one, no, you have del dot A plus 1 over C. It looks like this is some sort of partial over partial T of some phi over C equals 0. Now, in order to make sense of this equation, we can start thinking that because this is a temporal derivative, right? Temporal derivative through time. It would make sense if, it's not actually what if, no? But A is indeed a four-dimensional vector. No, we can think of A as a four-dimensional vector in which this is the zeroth element of A is phi. If we use that one, if we use the fact that A mu is what? Phi over C, and then A1, A2, A3. This is actually A0. A0 is phi over C. By the way, we write the vector this way, no? Pero this is I mean, kani siyang annotation is common, pero technically kabalutan nga kani siya is that A mu is not the whole vector. Take note of that, right? Because in fact, A mu is the component of the vector. And in many cases, even in the books, in some books, or I think some of the tutorial in YouTube, equate this two. It's not actually, they don't mean it to be like this, no? Only just to, pag four-dimensional manggod, in fact, the best way to write this is this. Because this is a vector field. But this one, the notation A mu, is what? A component of a vector field. Okay? But, ang ato na lang dire is that in order for us, because maglisod ba tagkato because we are in the four dimensions, so murag awkward nga musulat ta og some we usually leave the arrow for the three-dimensional vectors, no? So let's just write it this way, or maybe properly siguro butangan nato gana, because this is in fact a row, I don't know, column matrix, or we write it as what? Phi over C, A1, A2, and A3. This is a contravariant vector. Okay? A first rank contravariant, type 1, 0 tensor. Okay. And if we define A to be like this, then in fact, the Lorentz gauge is what? The four-dimensional gradient of the vector potential, right? The Lorentz gauge is actually setting the four-dimensional gradient of the vector potential into 0. That's the Lorentz gauge, no? Whereas the column gauge is actually setting the gradient of the three-dimensional vector potential into 0, right? I said the column gauge is del dot A equals 0. So how about this one? This is the same. This is actually the gradient. Sorry, not the gradient. Divergence. Okay? So setting the divergence, column gauge is saying that we want the kind of vector potential such that they are divergence-less. Right? It's our freedom. It's part of our freedom, no? So that's actually the column gauge. The Lorentz gauge is saying that, okay, the vector potential... okay. Muna, paminaw, gid mo no, kay grabe na, nangugat na ko dre. Okay? So, setting the column gauge, setting the divergence of the vector potential equal to the temporal derivative of the scalar potential, electric potential. Or, it's a combined, not only the electric potential, no? But it turns out that the Lorentz gauge is the four-dimensional version of the column gauge. This is the four-dimensional gradient. It says actually, while the column gauge says that the divergence, we want the divergence of the field of the vector potential to be zero, the column the Lorentz gauge is actually saying that, okay, the divergence is zero, but we are talking about here the four-dimensional vector potential. Okay? And electrodynamics, this works. For electrostatics, column gauge works. Okay? So, anyway, so we are now ready to develop relativistic electrodynamics through this one. Okay, we are now in the we're now in the world of four vectors. What's a four vector? You will read the four vector. That's actually what? A four-dimensional vector, no?